we will start with the semi-plenary talk of Dr. Olga Miroshkina from University of Dulsberg-Essen in Germany. Olga obtained her PhD in 2020 at the Condensed Matter Physics Department at Chelyabinsk State University. Sorry, I hope I pronounced well. During this time, Olga worked as a collaborator on 4 research grants and was a supervisor of 2 junior research projects. Since 2020, she has been working at the University of Dulsberg-Essen as a postdoc. Her research area is the prediction of the multifunctional magnetic materials and the fundamental understanding of their properties from first principles modeling. Today, she will present work entitled Effect of Disorder on Magnetism and Lattice Dynamics of Multifunctional Magnetic Heusler alloys, insights from the first principles. So welcome, Olga. We are very happy to hear you, and you have microphone.
Yeah. Does it work now? Can you hear me or? Sorry, can you hear me?
Yes, we can hear you, but we cannot see your screen.
Okay, 1 second. Please. I think I didn't had right before. Oh, okay. Can you see it now? Yeah. So.
Yes, but we see not in the presentation mode. So please.
Because it's not.
Now, perfect. Okay, perfect.
Yeah. Okay, thanks a lot for the kind introduction. Today, I'm going to present the result of my recent work, which was performed within the CIEEA 270 project in Germany. And I would like to thank, first of all, my PI, Markus Gruner, and our collaborators within this project, the group of Professor Heiko Wende. The group of Professor Heiko Wende from our university, the group of Professor Oliver Gutfleisch from the can you hear me?
Now we hear you. Yes, now we couldn't for 20 seconds.
Okay, sorry. I have no idea what happens, but yeah, I will continue with the acknowledgement, and I would like to acknowledge our external collaborators from the University of Parma and from the Czech Republic from, sorry, I can't really switch something. Can you hear me? Sorry.
Yes, we hear you. We see the presentation. All good.
Yeah, but I cannot switch the slides. I have no idea what happens. Okay, let's think that I acknowledge my collaborators, and my talk will follow quite classical outline. I will give some introduction, then just to give an impression, introduce the methods, and then pass to the results obtained with this method. I'm going to illustrate the effect of disorder on the magnetic and vibrational properties of nickel magnet-based Heusler alloys. And based on these results, I will make some conclusions. So the project on which I'm working on devoted to the hysteresis design of the magnetic materials for efficient energy conversion. And we aim here to find the new sustainable bulk magnetic materials at their physical limits and get a maximum hysteresis for permanent magnets and minimum hysteresis for the magnetocaloric materials. And I work mostly on Heusler alloys, which are considered as a prospective candidates to be used in both of these areas. So actually, what are Heusler alloys? These are ordered intermetallics with a generic formula X2YZ, where X and Y are 3D transition metals, and Z is the main group element. Nowadays, actually, there are several new subclasses of Heusler alloys, but today I will focus mostly on the classical ones. And why they are so interesting for the community? Actually, because they demonstrated strong coupling between the lattice electronic and magnetic degrees of freedom, and this allows for a flexible crystallographic and electronic structure. This flexibility, in turn, gives a rise for many functional properties, which maybe most of you know, and likes, of course, including, we can list several of them, but I want to stress on the shape memory effect, on the magnetocaloric effects, which are very interesting for the community. And the nickel-manganese-based subclass of Heusler alloys is of also special interest because such materials can demonstrate both first-order magnetostructural and second-order magnetic transition near the room temperature. And such alloys have a very rich and quite complex phase diagram. I just illustrate here the several examples by nickel-manganese-based alloys with tin, indium, and gallium as Z elements. And on top, you can see the composition, the Z element concentration, and on the bottom, the valence electron concentration. And we can see that these alloys, the ground state of these alloys actually includes cubic L21 phase, then 10M modulated phase, 14M modulated phase, and L10 phase when we increase the valence electron concentration. Yeah, but today I'm going to focus mostly on the magnetic properties, and all this series have a ferromagnetic ground state, but in the austenitic phase, they demonstrate the magnetic transition from ferro to paramagnetic phase at the temperatures close to the room temperature, and the Curie temperature of austenite is actually almost independent on composition, as you can see here by these black triangles. And the ferromagnetic ground state is determined mostly by the superposition of a short-range and long-range magnetic interactions between margins, which placed at the A sublattice, and nickel, which placed at AC sublattice. And margins atoms here provide the largest contribution to the magnetization. The dominant coupling is exactly this exchange between nearest neighbor, margins and nickel. But if we deviate from stoichiometry and introduce additional margins, this margin excess atoms goes to the Z sublattice. And the direct antiferromagnetic exchange between margins at for A sublattice, its own sublattice, and for B sublattice, the Z sublattice, can be established also in these alloys, and some competition between ferro and antiferromagnetic interactions occurs. And today I will mostly focus on the nickel, manganese, tin, and indium compounds. I will start from the ternary stoichiometric composition and then pass to the off-stoichiometric more complex compositions. And this investigation was performed by means of a theoretical modeling. And actually, theoretical modeling, of course, is extremely helpful and allows to study the effects, experimental study of which can be difficult due to different reasons. But of course, it's also not just a pressing a button and you got a very nice result, unfortunately. Theoreticians have to make a lot of efforts to develop an effective tools for such an investigation. And nowadays, one of the most efficient and effective tools is density functional theory. It allows to predict the materials, predict their properties, but which is also important to understand the mechanisms behind. And with density functional theory, we act at a nanoscale and deals with the systems of hundreds of atoms. This is the first principles method, and the beauty of this method is that we do not need here any experimental input, any fitting parameters. The only information we have is the information from the periodic system of elements. Meantime, the results of this modeling can be already used for modeling at different scales for the molecular dynamic, Monte Carlo simulations, and so on. And for Monte Carlo, I will show the results later, example of such a using. And what's the idea actually of DFT? The idea is to replace the 3 n coordinates of the system which is 3 spatial coordinates for each of n electrons, and we have a many electron system. It's a lot, of course. We replace it by only 3 coordinates of the electron density. This allows to decrease significantly the numerical cost of the task, while the accuracy and efficiency of the investigation should be provided by the choice of the exchange correlation functional, which is approximation for this term, for the exchange correlation energy. Unfortunately, I cannot go deeper into the details, but for those who are familiar, I want to note that this investigation was performed within the GJ approximation, but I also have some comparison with other functionals. If you are interested, we can discuss later. So, and now the question is how DFT help us to investigate the material's properties, and I will show you how it can be used to investigate the effect of disorder on the magnetic and vibrational properties of Heusler laws. And I would like to start from the stoichiometric composition, which looks actually quite simple at first glance. It's a ternary stoichiometric nickel-2 Margin-Steen. And for this composition, we performed the phonon calculations and obtained the vibrational dose. And within our project, we had a unique opportunity to compare our results with the results of nuclear resonant inelastic X-ray scattering. This comparison is depicted actually at this figure, and we can see that there is a quite good agreement for the low and middle energy ranges, but the agreement is less obvious for the high energy part. And to get a microscopic understanding of a particular features of the TIN dose, we firstly calculated and investigated the phonon band structure. So this is quite complicated plot. I suggest to, so to say, read it together. Please pay attention to the color code, and on the left side, the intensity of certain color indicate the strength of contribution from corresponding atom. And on the right side, it's depicted in a little bit different fashion. Here you can judge on the contribution by the height of the corresponding peaks. So actually, one expects that phonon frequency scales inversely to the square root of mass of the element, which means that the tin as a heaviest element should dominate in the lower energy range. And this is indeed the case for the range below 13 millieV. Here we can see the similarly strong contribution from tin as a heaviest element and from nickel, which just contributes here twice in terms of composition. Meantime, there is almost no Margin's contribution, which is also confirmed by the VDOS. The middle energy range is dominated mostly by nickel vibrations, while this yellowish stuff indicates an increase in Margin's contribution, and in the range between 18 and 23 millieV, we already encounter the first bands with predominant Margin's character. The high energy range can be characterized by equal contribution from all the constituents, which also can be seen from the VDOS. And here the strong coupling of individual displacement, which is actually seen from this non-primary and mixed colors, indicate that a collective motion with similar contribution from all the constituents characterize the top end of the spectrum. Generally, the situation then nickel vibrations dominates mostly in the middle range, while the the heaviest actually element also provide a large contribution to the high energy part, is a typical feature for almost all nickel Margins based Heusler alloys, and it was termed as mode inversion, which usually discussed in terms of soft transverse acoustic mode associated with cone anomaly and Fermi surface nesting. But if we go back to this comparison, we ask ourselves what can be the possible reason for such a deviation between theory and experiment, and we supposed that the disorder can take place in these systems, and it was actually also confirmed by the team with Bauer measurements. With several peaks at the low temperature measurements tells us that there are several types of tin magnetic moments, which should not be the case if we have a perfectly ordered structure. And to check this, we performed a modeling for the disordered system and introduced the anti-side disorder. So we swapped margins and tin atoms and margins and nickel atoms. And additionally, as a second, so to say, series of calculations, we introduced the magnetic disorder just by anti-parallel orientation of one margin's magnetic moment. So what did we have from these calculations? We can see that the disorder on the transition metal side changed significantly the tin VDOS spectrum and diminished the high frequency part of the tin VDOS, bringing actually this profile closer to the experiment. Meantime, the magnetic disorder doesn't help us too much because it goes hand in hand with increasing again tin contribution at higher energy part. Both this disorder, anti-side disorder in ferromagnetic and ferromagnetic cases also results in several types of tin magnetic moment in agreement with the experiment. Generally, with a disordered structure, we bring our results closer to the experimental one, but since the agreement is still imperfect, we can suppose that the real samples might be a subject of complex superposition of different structural and magnetic defects. So from this example, from this case, we learned that the tin VDOS are very sensitive to the magnetic and chemical disorder on the transition metal side, even if we do not touch tin itself. And the tin VDOS actually can be used as a probe of the order or disorder in these systems. So, but what happens if the disorder will come not just from the swapping between the atoms, but from the deviation of from stoichiometry? This is a little quite a complicated case, and to investigate this, we considered such a series with nickel deficient sub-lattice, and actually this series was chosen to maintain the austenitic phase down to the low temperatures, keeping meantime maximizing margins for B occupancy. So the margin excess firstly goes to the Z sub-lattice, but if you have nickel deficient sub-lattice, not the nickel 50 but nickel 48, some margins goes to it, this side, this red stuff. So, and our colleagues from Parma University performed an experiment and found an effective magnetic decoupling between the sub-lattices. Here, the 4A sub-lattice determine the Curie temperature of the whole alloy, and this temperature is actually almost independent on composition. Meantime, for B sub-lattice becomes disordered at lower temperatures if we introduce tin and increase its concentration. And the suggestion was that the frustration of a magnetic system due to competing magnetic interactions takes place in such a materials. And to provide an explanation for this counterintuitive picture, we actually use the density functional theory modeling. First of all, we should determine the magnetic ground state because we see this strong competition. And to get a very accurate energies, we have to perform the full relaxation of the systems, taking into account the optimization of the interatomic distances and lattice constants, which depends strongly on the magnetic ordering. And it is actually illustrated by this with relaxed structures. You can see that the changes in the position is only almost actually invisible in ferromagnetic case, but they are already moderate in paramagnetic case and very visible in antiferromagnetic one. So this means that we should, it's necessary to take it into account to get a very accurate energies. And from the comparison of the total energies, we found that there is a composition-dependent competition between ferromagnetic ground state, which is a characteristic feature for the indium-rich side, and antiferromagnetic case, which is the ground state of the tin compound, fully tin compound. And this was the result for the nickel 50 composition if we do not have here margin excess. But if we introduce this excess, it stabilizes a ferromagnetic solution with respect to antiferromagnetic one because antiferromagnetic curve goes up. Moreover, it shifts the crossover between ferro and antiferromagnetic ground states towards higher tin concentration. Taking into account this close competition in the middle of a phase diagram, and we can see that here the difference is also only several milli-eV, we can suppose that the margins for B, which has only nickel as a nearest neighbor, might prefer antiferromagnetic orientation, while if margins for B has at least one margins on nickel sublattice, if we have this red stuff here, it might prefer ferromagnetic orientation. And we simulated the complex and homogeneous, so to say, magnetic configuration with ferromagnetic clusters in antiferromagnetic matrix on 4B sublattice, and found that this configuration is energetically more preferable than purely antiferromagnetic one because it's lower in energy, and moreover it shifts back the crossover between ferro and antiferromagnetic ground states in the middle of a phase diagram in agreement with the experiment. Of course, also for these systems, we investigated the magnetic moments and found that they depend only moderately on composition, which actually means that the reason for the competition between ferro and antiferromagnetic ground states, and thus for the decoupling of the sublattices, should be found not in the magnitudes of the magnetic moments, but mostly in the interactions between them. And to investigate this, we calculated the Heisenberg exchange constant and studied from the nickel 50 composition. By this example, we already can see that such systems are under the competition between ferromagnetic margins nickel margins exchange and antiferromagnetic margins exchange. And the strength of both these exchange can be tuned by the tin concentration. We can see if we introduce tin in the system and increase its concentration, it weakens ferromagnetic nickel margins exchange and strengthens antiferromagnetic margins for A, margins for B exchange due to the increase in valence electron concentration. And so the nickel 50 system is, in this system, for A sublattice, determined by the ferromagnetic nickel margins for A exchange, while the for B sublattice is under the competition between this ferromagnetic nickel margins for B, in this case, and antiferromagnetic margins for A, margins for B. And actually also the, as I mentioned in the introduction, the magnetic moments of nickel are also determined by margins atoms, and they are larger in ferromagnetic case than in antiferromagnetic one, which actually leads to a stronger exchange between them. Thus, also both ferro and antiferromagnetic configurations can be metastable in nickel 48 composition and may even coexist. Now, as I mentioned, I want to show you that the results of DFT modeling can be used as an input for other methods. And our colleagues from Parma University took our exchange constants and used them for the Monte Carlo simulation to get a very nice, actually, phase diagram, which agrees well with the experimental phase diagram. From this case, we learned that for A sublattice in nickel margins indium and tin system is long-range ferromagnetically ordered and defines the Curie temperature of the whole alloy, which is actually depends mainly on the exchange between margins and nickel atoms. And for B sublattice here, which is only partially occupied by manganese, orders at Curie temperatures, which decreases when we introduce and replace indium by tin. Thus, the decoupling of the sublattices is not a direct consequence of a magnetic inhomogeneity introduced by margins on nickel sublattice, by this red stuff, but mostly due to a change in the intersublattices interactions. From this case, we learned that the composition-dependent competition of ferro and antiferromagnetic coupling can be tuned by the main group elements. And this is very actually beautiful because the exchange of between main group element and other elements at all is very small, but a main group element indirectly affects the exchange between the transition metal atoms, which is large, and determine the magnetic ground state. And this can be employed to control the magnetization of the transition metal sublattice. This brings me to my conclusions. I showed you, sorry, I can't yes, I showed you today how the disorder on the transition metal side can affect the magnetic and vibrational properties of nickel manganese-based Heusler alloys. Such a disorder strongly affects the TN-VDOS profile and diminish the high frequency part of the TN-VDOS, providing a better agreement with the experiment. It also results in magnetic inhomogeneity in the stoichiometric nickel to marganstein. And in combination with variation of the main group element, the disorder on the transition metal side allows to control the magnetic order on different sublattices in off-stoichiometric quaternary nickel manganese indium and tin alloys. So I hope I convinced you that the redistribution of the transition metal atoms caused by either anti-side disorder, either from deviation of stoichiometry, allows for the fine-tuning of Heusler materials properties and increase, in this sense, the range of their potential application. And with this, I would like to thank you for your attention.
Thank you very much, Olga, for this amazing, beautiful presentation. That was excellent. I don't know if we have any questions in the chat, if someone is raising their hand. I think I will start with the question then. Maybe someone will comment later. So I am experimentalist, so maybe my question will be a bit funny for you, but I am very curious. So if you tell about the all of your work and then comparison to some experimental results, could you please, do you know what is the method of manufacturing these materials? Because it seems to be like very advanced in my understanding. How does it look?
How the materials were synthesized, yeah, actually.
Yes, the manufacturing, like if you know.
It's a good, actually, of course, question. I unfortunately maybe cannot comment now directly because I worry that I can tell also something quite funny in this sense. But yeah, it's quite advanced, I think, techniques because in our project they have really the group of Professor Oliver Goodfleisch. They have a really nice methods. Maybe I can recall during the next questions and comment.
Okay, I will try to find you maybe if you will join Gathertown or somewhere here. And then... Okay, but thank you. It was just curiosity.
What I remember, I think the nickel to marganstein, the stoichiometric composition was prepared by arc melting. But for the off-stoichiometric, I should recall actually.
Okay, don't worry. It's just a curiosity question. Okay, and if you have, we have some question. Yes, we have. So from Flavia Gomez, very nice talk. Could you please give some details on the MC simulations?
Unfortunately, not too much, because as I mentioned, it also was not our calculations. We just performed the DFT calculations and gave the results to our colleagues from Parma University. I can just tell that they took 1 hour exchange constant. I think it was antiferromagnetic 1. And here, maybe I don't know if it's helpful, but how actually these phase diagrams can be related, so to say. They simulate this composition by the appropriate ratio between ferro and antiferromagnetic exchange constants. By this ratio, they simulate the composition, and it allows to get this nice actually phase diagram.
Okay. Flavia says, thank you. Okay, we have to move for the next talk. Thank you very much, Olga, for this amazing talk.
Thank you for your attention. Thanks.
There is another question. Could you have a look in the chat, maybe an answer in the private chat, because we will switch to the next talk.
I'm not sure that I can open it. Unfortunately, again, I have some problems.
I will send you.
I mean,
I am copying now. Okay, so I will send you. You could discuss. Then we will go to the next presentation, to the